two DC motors that we haven't talked about that we use a lot in manufacturing. One is called a stepping motor. And then another one, which is becoming very popular, it's called a brushless DC motor. Brushless. Huh? Oh, yeah. I'm sorry, I just didn't turn on the
Is that what people talking about, two-step motor, Mr. Rick? Right here, and like, my old job thought a two-step motor or a two-phase motor, is that a?
No. That depends on a two-step motor would probably be a two-speed motor. Like most JCA systems use a three-phase AC motor, but you don't control the speed in variations. You control it in steps. And when we get into AC motors, you'll understand how we can control the speed in steps. A stepping motor, I'm looking for my. A stepping motor basically rotates in steps. This is a stepping motor. What I want you to do is just turn the shaft on the thing sticking out. So what a stepping motor consists of, it consists of a permanent magnet rotor. Permanent magnet rotor. So this is a permanent magnet. That's just what the coil, that's what it would measure with the ohm meter. So we have 4 coils inside this thing, at least 4, the way we connect them together. I'm sorry, we always have 4 coils, but it might have more field pole pieces. And what we do is we electronically move the field around the outside.
That's the one you were talking about, that if you move.
Well, that's what I'm doing. What we do is we can control its position by controlling, but notice, I want you to notice the thing moves in steps. So what happens is we move the field a little bit, and what does the permanent magnet motor do? It rotates to align with the field, right? You understand? Then we move the field again, and then it rotates to align with the field. How fast we move it around would depend on how fast it runs, but when you turn the shaft, you can actually feel the steps. We call that the detent torque, where the magnet actually locks into these. So this is metal, this is a magnet. So when you turn it, you can actually feel the field poles latching into the poles. Now that's only a 24-step motor. When we talk about the number of steps, that's the number of steps we have per revolution. So that guy right there would have very poor resolution because it's only got 24 steps. So that means we calculate what we call the transfer function, and this would be how many degrees would it move per step. Well, what I would do is I would take my outputs in degrees, and there's 360 degrees per revolution, right? Understand? And then I would divide that by the number of steps. So every step it would move that many degrees. So the more steps the motor has, the better resolution it has, the more accurately it can represent a position, right? So what would be our steps per degrees? Or the 24-step motor? Huh?
What do you mean?
There's 360 degrees in a rotation. We're going to move this thing in 24 steps. So how many degrees would they be per step? So what we call the transfer function is always what we got out by what we put in. So yeah, so that guy would be the transfer function on this would be 15 degrees per step. So I would be able to do 45, I would be able to do 90, but I couldn't do 20, right? You understand? Because it would be between a step, right? Does that make sense? Unless we do something fancy, we'll look at it in a minute. This is what we call a unipodal portal stepping motor, which means we have 4 coils, and then what we do is we have an electronic circuit that we come up here and then we switch it on. So these are NPN transistors, and we're using them as switches. So what happens when I put a pulse in here, this guy here acts like a closed switch. And then when I take it out, what we get out of a transistor is we get a lot more current out than we put in, right? It's what we call it's a current route. So we have to electronically control this motor. We just can't turn it on. We have to add electronics to it to do this, right? Does that make sense?
If the roller is magnet, then how, where's the pole of the magnet? So, to make it.
I wish I could find my big motor. I can't find it. We have a sure enough stepping motor that we have taken apart, and you can actually pull that sucker out and you can see the field poles. Well, basically, it's just a magnet that's made in rotors. And this was the blue, red. I don't know what they're using, but one of them would represent a south and one of them would represent a north, right? You understand? So what we do, if I come over here and make this one, if red is a north, I'm gonna make this a north and I'm gonna make this a south. Well, what happens over here, all the blues are gonna line up over here. I'm sorry. That's not exactly what I want. So what we're doing is, yeah, they would be opposite of each other. And what would happen is they would line up. And then what we do, we would do what? We would shift it. We would turn these guys here off and then turn these 2 guys here on. And what would it do now? It'd take 1 step. And then what we do is we're going to come up here, and this is not exactly right. So this is the way the unipolar works. This is not a unipolar that they're showing. Well, it is, but what we would do is, so that was right. The south-south would be right. So what would happen is the way we get the magnetic field is the way we put the current flow through it, right? So notice what we're doing is I would come over here on this, and let's say I turn on this transistor right here. But what that would do is that would make this guy right here, and since the current flow in the same direction, that might make this a north, but it's also going to make this a north. They're not opposite of each other because we're only controlling both sides, right? You understand? So what would happen if blue is south, then what's going to happen? The motor's going to turn until the south lines up on both sides, right? Does that make sense? Because these 2 are wound together. They don't show that, but what happens is these 2 are wound together. And then what would I do? I would come over to the next one, and the thing would do what? It would turn and turn and turn. And we call this a unipolar. What's nice about a unipolar is it's very easy to control, but we don't get as much torque. We would get more torque if we did a north on one side and a south on the other one. So what we're doing here is we're just pulling the motor in one direction, right? You understand? What we would get more torque is if we did what? If we pulled on one side and did what? Push on the other. To do that, which this guy don't really show, is we have to have what we call a bipolar. So a bipolar, what we do is all 4 windings are wound. All windings are wound separate of each other. So they're not common on one side. Does that make sense? And what we can do now, we can electronically switch the 2 poles, and we can do a push and pull on both sides. The biggest problem with a bipolar motor is that it's a lot electronically hard to control. This is the electronic controller that controls a bipolar system. Now, what we can do, I don't know if you're seeing what's going on here, is this is neat. What they're doing is they're actually activating 2 coils at the same time. And what happens is your rotor comes up and aligns in the center. We call this half stepping. So if we come up here and enable two poles at the same time, then the rotor would move in the center, right? You understand? This is called half stepping. This takes pretty complicated software, and also it takes a pretty complicated circuitry. But you can buy what they call half step controllers, that you buy the circuitry, and all you do is send pulses to it. What's nice about half stepping is if you got a 100-step motor, which is what I've got up here, we would literally we could get 200 steps out of it. This makes sense? Kind of looking confused. Gilbert, you okay? So you see what they're doing here is they're energizing this one and this one. And then what they're doing is they're energizing this one and this one. Well, when they do it, the equivalent magnetic field is going to be where? In the center. So what it does is it moves in the center. This is called half step. And they can get very complicated with this. And they can do what they call microstepping, where they come in and energize a lot of them at the same time, and what the rotor moves to where all the addition comes into play. So I've seen microstepping where they can get 18 times the number of steps that's available on the motor. But what you got to do is you got to have a bipolar, so you can control all of the coils on both the top and the bottom instead of one polarity. Does that make sense? I basically built I've got mine. This is a pretty common motor where you can wire it as a bipolar or you can wire it as a unipolar. And what you do is let me bring my camera up. So this is my stepping motor. So you look on that one, it's got 5 wires, right? Or does it have 6? The one I passed around. Where's it at? Huh? Who's got it? Okay. Yeah, this is the one, this is the wires. So here's my commons right here. If it has 2 commons, this means this is a bipolar stepping motor right here. So this is the brown wires, these are the commons. And then these right here are the actual coils. So if I twist them together like they were, then we're running this as a unipolar stepping motor. This makes it real easy to control, right? You understand? If they're split apart, then they would go to different places. And this would be what we call, this could be a bipolar stepping motor. So when I look at this one, it only has 5 wires on it. My thing zooms in, if it focuses. This one has 5 wires on it. So this right here is a unipolar stepping motor. Unipolar. Unipolar means it's only got 1 common. So what happens is we run back into this circuit right here. So this would be that brown wire right here, right? I understand. What they do with the bipolar is two of them will have the same common, but I go from a common to this up here, right? You understand? Does that make sense? And I can only energize 1 or 2 coils at the same time. That makes sense? Okay. So if it's got 6 wires, which is what this one does, then this right here can be wired as either a bipolar or it can be wired as a unipolar. So if I want to wire it as a unipolar, I would take these 2 brown wires and I would just connect them to the same spot. If I want to do it as a bipolar, then these 2 brown wires would go to different spots. So a 5-wire stepping motor, which is what this is a unipolar stepping motor, which means I can't wire this as a bipolar. So bipolar we can control more precisely, but the electronics gets what? Really complicated. Oops. This is my wiring. This is, so what I did is I wired, so this is a circuit that we designed to run the stepping motor. But you can buy these now in one integrated circuit, stepping motor controls. You can look it up on the internet. You can buy the controller for the stepping motor. You can program it to run with software, but normally they have a circuit that does this. This is nothing but a digital counter. So this comes up here. What I'm going to do is I'm just going to put pulses in here. For every pulse I put in there, it counts. But then I'm using 2 digits in that to output a binary count. Then I'm converting that over to this, and then this is the driver right here that runs the stepping motor. And then notice I have the 2 brown wires connected together when I run this guy right here. So I'm running this as a unit. Like I said, odds are you wouldn't design your own circuit. You would go ahead and just buy the stepping motor controller, right? Does that make sense? And what's neat about that is you have to come up with a circuit that puts pulses into it, and then normally you got one that determines the direction. So to change the direction, all we have to do is change the rotation of the field, right? You understand? So this is the circuit. I'll have to wire it up. So I'm running this with a microcontroller. This is my Arduino. And I think I showed y'all that last class, right? Yes or no?
There we go.
Yeah. So we have these PLCs. So
You showed that.
so the PLC, most of your PLCs, they have what they call a pulse train output, which means it just sends a bunch of what? Pulses. So we could use one of those to make the stepping motor stay up, and then we can use another one to tell it to change direction. But then I would have to I would pay all this money for a PLC to run nothing but a what? A stepping motor, right? You understand that? So what we have is we have these little microcontrollers right here. I can get this thing from Jamico for $30. So I've got 2 options. I can pay a couple $1,000s for a PLC, right? And then pay RS Logix $5,000 if I'm a company. That's about $18,000 a year to license that software so I can program my PLCs. So here it would cost me $18,000 to buy the software to program a $500 PLC. Or I could come in here and buy this $30 controller, right? You understand? But it's not going to, in the programming language for the Arduino, it's open technology, so the programming language is free. You was leaning back and had your mouth open. But I got to learn how to program since it's very, very simple. I have to learn how to program in another language, right? Y'all understand that? So yeah, you can go up there if you want to play around with this. Like I said, Jamico sells them for $20 or $30, and then you can go online and download the programming language. But if you've never done, it would take a lot of research, guys, but there's a lot of stuff out there that teaches you how to program in the language. And then plus there's thousands of libraries already out there where people have done what? Written programs to do things for you. And so as soon as this loads up. unipolar are the types of stepping motor. So they're both stepping motors.
Bipolar is more precise.
Right, because we can control it more precisely. So a bipolar, we can one of the big advantages is you get more torque. So what we're doing on a unipolar is we're only activating one field, right? You understand? And it's going to pull on one side, and basically it's going to pull. What we do on a bipolar is we use two fields. Does that make sense? So this would be a north and this would be a south. So what we're doing with a bipolar is that we get more torque. So what we do is we bring all of the poles out separately. This is not a good image. But what it takes a lot more complicated circuit to run a bipolar stepper. So this will control one field. This will control the other field. You can see it's very, very complicated. These are, by the way, these are industry standards, our ISO standards for logic. Hopefully, whoever teaches you also we can use the international symbols for the digital gates. Next semester, yeah. Yeah, but the triangles are the same as the bubbles on the standard gate. You know, these look like they're comparators greater or equal to 1. So these are nothing but exclusive ORs or exclusive NORs. Here they don't show the common. So this is a Arduino. This is the program that I wrote to run my stepping motor. And you see it's not something that somebody could do just go out and do that. It's very similar to programming language. It's very similar to Pascal. If you ever played around with that programming, it's a text-based language.
So you use the laptop.
No, you need it's just like a PLC now. Used to, when we first got into PLCs, the PLC had all the processing power. It did everything. We hooked up what we call a dumb terminal to the thing to program it. Over time, what has happened is that we've done away with that. The PLCs have got a lot cheaper, so the PLCs, we can't program the PLC with the PLC. We run an application on a computer that allows us to program the PLC. Okay. So this is true here. So this is just a program that I use to program my Arduino. And then after that, I can turn the Arduino loose on its own, right? You understand? It runs the program. Does that make sense? So you need a computer. The Arduino is this little microcontroller right here. That's the name. That's the name of it. That's that little thing right here. This is the Arduino right here. And it's got inputs. So all this on this side are inputs. So it's got 14 I/O ports, which means these are programmable. So on a PLC, most of your ports are either input ports or output ports. What we do on the Arduino is we program it to be either what? Input or output or bidirectional. So we can program it to be a true I/O port. So when you say you got 13 ports, you got 14 ports, that's up to you to program. Huh? Like a baby PLC. And then over here it's got 5 analog ports, which you can program to be either what? Analog in or analog out. This is the actual microcontroller right here. So basically this is a tiny PLC, but it doesn't program in ladder. It programs in more what we call in PLCs. It would be kind of like structured text programming, which a lot of people and what they're trying to do with PLCs, of course, is I talk about this in my class, is give people the ability, no matter what field you came up through, the ability to program these things. So ladder was originally developed for electricians because they understood motor control circuits, right? But then you got people that came up through the computer world and they understand this Pascal, they understand all these text-based languages. Well, that's what the structured text language is. So this is very, very similar, guys, to what you would have to know if you did what we call structured text programming. Very, very similar. So if you came up through that, you'd rip up an Arduino. That would be the route you would go. But if you come up through motor controls, then you're going to have to learn the language. PLC. But here you have to type everything in. You can't just go up there and pick a symbol. You have to tell it. Yeah, every bit of this. Yeah. So you have to come up here and you have to initialize the ports. You have to come in and call them output pins. You have to set up the speed that you want to communicate with the Arduino. So yeah, but we're using this as 2 things. Not only are we, and then though, but you could set up a communication port where you could literally communicate with the Arduino through a PLC. So the PLC could tell the Arduino to do something, right? Or we could have a panel up here. It's just that you have to learn the language of how to program these things. That makes sense? Huh? But good gracious, guys, you're talking a difference between thousands of dollars and what? $30. So yeah, you'll run into a lot of these, but usually they run dedicated tasks. Once they've been programmed, you probably don't ever do what? You don't ever reprogram them, right? Does that make sense? So
why are some of it like solar?
These are all comments. If I start off with an asterisk, this means these are just comments. And normally we use a bunch of comments, so when I come back in here, it tells me what I need to know about this program. It tells me where to go to get the wiring diagram, how to wire it up, and stuff like that. Yeah, it says the stepper motor circuit requires an external 5-volt supply, right? The sketch requires a hardwire stepper motor circuit in AUT 208 handout folder. So it tells me everything I need to know where to find this stuff so I can go back up and hook this up every semester. So anything that's grayed out, that means that these are nothing but what? And also, not only grayed out, I'm sorry, it starts off with the backslash. And then it ends with a backslash. So all these out here are comments. You see these double backslash, these are nothing but comments for me to do what? Know how this thing's supposed to run, because that means I don't have to go back in here every time I show you all this and do what? Look it up. It's all inside. It tells me where I need to go and get this wiring diagram I just showed you, or the actual circuit that runs it. It tells me I need to run this thing on a 5-volt supply. It tells me that the maximum number of steps I can put in here is what? 65,536, right? That makes sense? Here, this is not in degrees. This runs in steps. So that's the maximum number. It's using a 16-bit number to keep up with the steps. So right off the bat, I know if I put anything over 65,536. So how many rotations would it make? Well, with this program, this is a 100-step motor. And what I'm doing is I'm going to enter the number of steps. So if I enter 100, we should just see this thing make what? 1 revolution. And it's going to do it. It's going to do it in steps. I'm looking for my USB cord. because I got to download the program into the Arduino. So the Arduino itself will run off it'll run off a 5-volt supply, or it'll run off, it's got a little regulator on it. You can run it off a 9-volt supply too, or you can run it off a 9-volt battery. So all I have to do is power it up and just hook it up to my USB port. So where'd my Arduino go? Oops. So this is where you would power it up off a 9-volt supply right here. And then what you have to do is you have to establish if you're going to run it with an external power supply, which I am, you have to establish a common with your external power supply. So that's what this wire is right here. This is my common. You understand this? And then of course what I would do now is I would hook up my 5-volt supply to my circuit. I'm not using the Arduino to change directions, which I could. So what I would do on my circuit is right here. So if I flip this switch, it would run in the opposite direction. Well, I've just got it jumped out right now, so I'm going to run in one direction. But I could output something on my Arduino that would change this right here and either make it go up or go clockwise or counterclockwise. So right now I didn't put that switch in there, so it's fixed. Started at a known position, then the steps mean nothing, right? You understand that? A known position. So we have to set this at robotics. We call it an origin. We have to, we have home. Well, not necessarily home. Origin and home are two different things. In robotics, normally home is where you park the robot at. So if you go over there and look at the big Fanuc robot, it is at home position. All it is you park it so it's not in the way of the line. Origin is where you set the encoders to 0. That's your established point. So right now, if this means anything, if I started this out here somewhere, it don't mean anything. But if I start it lined up with one of these bolts as close as I can get it, and then I come in here and I type in 100, then what it's going to do is it's going to make what? Exactly 1 revolution. If I type in 200, it's going to come up here and do what? It's going to make 2 revolutions. But it's going to stop at exactly the same place, right? If I type in 50, then it's going to go 180 degrees. Right? That makes sense? 25 would equal what? 45 degrees. So I could do the math. I've got another program where I enter the degrees, but all it is doing math, right? You understand? Saying 100 steps equals 360 degrees. But so 50, you know. Well, it all depends. Some robots use stepping motors, but they also use encoders too. So because they got to be so precise. Because what would happen if I come over and did that? Now I'm screwed. Because now I've lost my what? Huh? I've lost where I'm at. Yeah, so some robots use stepping motors because we can control them precisely in steps. But then they also have encoders on them so they get feedback to know if something's what. Yeah, if it's moved from where it, yep. And it'll lock it down. So if you come up here, If you try to push on a robot, most of them won't move because the encoder turns and it automatically feeds back. So we do have stepping motors that do have feedback.
So that's kind of like it works. You got the robot cell and the robot, you had this fixture where we put the parts in. So before the robot even will, it'll reset the fixture back to its home station. And then it'll rotate it, then the robot will weld it. So you think that has encoded in the 2 and 3?
Oh yeah, the actual fixture itself, the stand. Robots, most of your robots are what we call 6-axis robots, but a lot of your controllers can control more than 6 axis. These would be external axis, like you're talking about, where you could actually do what? You could actually program rotating that 7th axis around. So yeah, 7th axis. So you might see a robot that's on a section of rails.
Yeah.
And that move. Well, that would be a 7. That would be a controller that can control more than 6 axis.
Yeah,
He's
he'll
got
slide up and down the little rail. Yeah.
So this is what's so neat about a stepping motor. We can run it open loop and get very accurate as long as we don't stall it, right? So if I was to come up here and tell it to go 100, then I come over here and I grab it, it sends it 100 steps, but it's what? Yeah, it's screwed, right? You understand? So if you stall the stepping motor, you're in a bunch of trouble because it loses its orientation. So yeah, they do. We do run some robots use stepping motors, but they all have feedback. So if I did come up here and install it, it would know right off the bat it's sending it counts and it's not getting information back that it did that it moved it. But a lot of
My job, when you crash a robot, you have to send them the origin, big holes into it, and it'll take the put it right in the middle of that hole. Then now it knows where
well, that's not really the origin. It's probably finding the tip of the weld. Yeah, usually origin on most robots is like this, 90 degrees, the origin. Except for the KUKA. The KUKA is laid out on its belly. That's when you get 0 back from your encoders. But what you have to understand, and you might be right, is that that's what we call factory origin. So if you go over there and look at all our robots except the KUKA and the Big Fan, it's parked 90 degrees. So it comes up and then but it's really up to the people who use it to determine what the origin is. But what I'm saying, if it lost its origin, it couldn't find the hole. So what it's trying to do is figure out what's going on with the actual tip. What's going on with the tip. You'll see some robots that wire welding robots, between every piece, they'll swing around and it'll drop down and they'll clip that wire off to the exact right length every time. And that way it knows exactly where to start. Because what happens, you go out there and you strike an arc, and what happens, the wire changes its depth. So that's probably, it sounds like what you're doing. Yeah, if it lost its origin, it wouldn't be able to find the hole, right? Right. So it's probably just figuring out where the tool's at again. So this is a stepping motor, guys. You're going to run into these things all over the place. For one thing, we can run them open loop. Just about if you got an inkjet printer, that's basically what it's using to position the head across the top to actually do the print. And also usually the paper, it actually uses a stepping motor to position the paper. How far does it go up, right? When you come up, it comes up a certain number of steps. Those are usually open loop. No, you just call it, they call it a certain, well, technically they'll probably call it, it's probably kind of misleading. They might call it a servo motor. A servo motor is a motor that provides feedback. But it could be a stepping motor. Usually a stepping motor will sing at you when it runs. It'll go, because what you're actually hearing is the water. You're actually hearing the steps as it comes in on each one of those poles. We can run them, but we call it the slew rate. So I could increase the speed on this where the stepping motor couldn't keep up with the pulses. So a stepping motor, if you run it at its slew rate, it'll look like a regular motor. because you're running it as fast as it can step, right? You understand? Or you can run it real slow. If you try to do that, then the stepper motor will lose its count. If you try to run it faster than the slew rate. So I can increase my delay and cause it to screw up. I don't know where my delay between pulses is right here. So this is off time, this is on time, and what I'm doing is I'm generating a square wave. So I leave it off for 9 milliseconds and on for 9 milliseconds, and it generates a square wave pulse. If I come up here and drop that down, let's say 5. I probably played around with this, guys, and got it running as fast as it could possibly run and still be accurate. So if you try to run a stepping motor faster than it's designed to run, then it will. So what I'm doing now is it'll miss steps. It'll start skipping. It'll be really, really bad. So if you see a stepping motor skipping, it usually means either they've lost one of the phases, right? You understand? Or you're trying to run it faster than it could possibly run. So you got the mechanics of the motor, and the mechanics of the motor will only run so fast. Yeah, so I just did that. So what I did, of course, is I played around with this thing. So now I've lost my accuracy. So if this camera updates fast enough, sorry, wrong. Let's see the motor, how jerky it is. And notice it didn't go back to where I started it, yeah. So what I'm trying to do is I'm trying to run the stepping motor faster than it'll run, so it's actually missing steps. I told it to go 1 revolution, right? You understand? So what I've done is I played around with this until I got it to run as fast as I could run it. This is the progress of the download, which Arduino calls it an upload. So that gets you kind of confused for a while. And then this is just a little application that I'm using to send information to it. So this would be like your panel that you're using to tell it what it wants to do, or your PLC telling it what to do. So it should be accurate again. Oops. I just can't look at it. Well, that's a stepping motor, guys. Really, of course, I got my thing in front of it. Y'all can't see it. But these guys have to be electronically controlled. So a DC motor, you know, you could put a DC motor across the line and it will run at a certain speed. If I want to control the speed, then I can electronically control the speed. But a stepping motor, you have no option. You have to do what? You have to electronically control it. So all I have to do to change directions is, and now it should run in the opposite direction. So it's real easy to control the direction on them, right? And you see, they're really precise as long as you don't stall them. So what I'm doing is I'm using a counter. This is an up-down counter. So if I put a 1 into this, which if we're doing it by default, it's going to count down. If I flip this switch, I don't have a switch, then it's going to count up. And what I'm doing is I'm changing the output of this over here. This is taking a count and converting it over to a string right here. And then this is my driver. This is nothing but a bunch of transistors in there. So this is basically this circuit right there. So it's an LM2003, and it's got 8 of these in there for me. So I'm only using 4 of them, but it's got 8 of those transistors inside this one IC. So this guy is the counter. Sorry, let me get my. So all it's doing it counts from 1 to 15 or 0 to 15, but I'm only using 2 of them because all I need to go is from 0 to 3. Does that make sense? Because I've only got 4 poles. This IC is taking the count and converting it over to a string. And this is the driver IC right here. So this little guy right here has got all those transistors in it. My Arduino could not run this stepping motor, or this encoder could not run my stepping motor, but this guy right here can. Does that make sense? So what this is, this guy right here is nothing. This guy here is nothing but counting. It would count to 15, but I'm only using 0 and 1, so it'll go, 0 and 2, so it'll count from 0 to 4, right? 0 to 3. When this guy sees a 0, this output goes true. When it sees a count of 1, this output goes true. When it sees a count of 2, this output goes true. When it sees a count of 3, this output goes true. And then what does it do? It just starts over. This is taking that and converting it over to an output. It's providing a 0, so I have my stepping motor connected to 5 volts. All I have to do is change the direction of the counter. So instead of going 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, if I tell it to count the other direction, it goes what? 3, 2, 1, 0, 3, 2, 1, 0. All this encoder does is just take whatever count I put into it and activates an output depending on the count. I told my counter to count down instead of counting up. Flipping this little switch right here. Well, I didn't actually flip the switch. No, I just told it to count down. You're thinking about Allen Bradley PLCs. So what would happen if I count up, and I'll do this with a counter, a true counter.
I get it, I just don't know how you say, how I understand how it works, but I'm watching you put 100 in there, then I'm watching this go 100 steps, right?
Right.
So then when you put it in the HMI your program to say, okay, count them back.
Well, it don't count backwards. All I'm doing is counting. All I'm doing is sending pulses. So when I come over here, when I put in 100 over there, what it's doing is it's sending 100 pulses. That's all it knows. It don't care. It don't care. It's just 100 pulses. Now we're only dealing with 2 bits. So if I count this direction, 2, 3, and then what would it do? Then it roll over. Okay, so this would be counting up. If I tell it to count down, no matter where it's at, if I tell it to count down, it's going to go like this, and then it's going to go like that, right? 3, right? Understand? And then it's going to go 2, and then it's going to go 1, and then it'll roll back down to 0. Well, all that other chip is doing is taking this count and generating an output. So if it sees a 0, this output goes true. If it sees a 1, this output goes true. If it sees a 2, this output goes true. If it sees a 3, this output goes through. So if I'm counting forward, it goes 0, 1, 2, 3, 0, 1, 2, 3. So my coils would be enabled 0, 1, 2, 3, 0, 1, 2, 3. If I tell my counter to count backwards, it'll go 0, 3, 2, 1, 0, 3, 2, 1, 0, 3, 2, 1. So this would go back. And what I've done is I've changed the direction of the rotating of the magnetic field. That makes sense? So what you got is you got an Allen Bradley counter, a down counter in your mind, which we have to load with a negative number. This is just a digital counter, and it don't give a sign. It just either counts forward or it counts what? Backwards. Yeah, well, I don't have a switch. All I'm doing is taking this black wire.
Oh, okay.
Yeah, so see this black wire I have sticking up in there right here? So right there, so there it is right there. Okay. So I've got it up. So now it's going to count in one direction. So now it's going in that direction. I'm going to take this wire and plug it in right there.
When you put the common,
No, it's not a common. It's just telling it instead of counting one. Well, you're right. I'm putting a 0 there. So we're getting into more detail. Yeah. So if I don't close that switch, then I'm putting a 1 right there.
what I was asking was, you put the wire in, that's what I didn't see, that's why I was.
Okay. Yeah. And when I flip this switch, it puts a 0 there. But what you got to understand is I could take this switch and I could use an output on my PLC to do what? Put a 0 out there and it would count one direction, or put a 1 out there and it would count another. So if you look at a stepping motor controller, usually it's got count in and it's got direction. You put a 0 in there, it might go clockwise. You put a 1 in there, it might go counterclockwise. That makes sense? Now the next motor is becoming really, really popular because it has no brushes. This is an old 5 1/4 inch floppy drive that we used to run. That we used to use before we had hard drives, right? And here's the motor here's the motor that would actually spin the disc that was inside here. And when I take it apart, what we have is we have a magnet around the outside. So it's real weird is that the magnet runs around the outside. So this is the rotor right here, or this is the center guy right here. And of course, it's got thousands of little magnets here. 1, 2, 3, 4, 5, 6, 7. They're beside each other, right? You understand that? And then what happens is we electronically spin a field around here. So this guy's got to run on electronics too. But instead of moving in steps like a stepping motor does, this guy actually runs it real smooth, right? You understand that? Now, what's the advantage? What's the problem we have with brushes? Why don't we like brushes? They're what? They wear out, but that's in electronics. We hate brushes in electronics. So you'll never find a brushless DC motor inside a computer. I'm sorry. You'll never find a brushed DC motor inside a computer. Why is that? Well, guys, what we got is we've got these little old commutator back there. And that commutator is doing our switches. And of course, this is insulated. Well, what do you think happens when that brush moves across that gap right there? It creates a spark. Anybody ever looked at a motor? When it creates a spark. The first radio transmitters we had was what they call spark gap transmitters. And when they was doing Morse code. So all they do when they hit that little button, they'd generate a nice big spark, and that would send out this electromagnetic interference out across long ways. And then we could pick that up. So the problem we have is with brushes is they generate all kind of what we call EMI. What's EMI? Interference. And I think I showed y'all that the other day. I was running this low motor right here, and my stepping motor was jumping all over the place. Because EMI off these brushes got into my counters and was making my counters count weird, right? I remember showing you that? I don't know if we can do it again. So the problem we have with with brushed motors is they generate all type of electromagnetic interference, all type. I don't know if it'll do it this time, but man, it was going crazy the other day. You know, see my step motor? All I'm doing, guys, is bringing this guy down close enough. This has got brushes, right? You understand? It's got that commutator, and it's getting into the electronic circuits that's running my what? My motor, because of what we call EMI, electromagnetic interference, right? You understand? Now, I could come in and I could shield this circuit over here, but that's going to cost a lot of money. Or I could shield the motor, and it costs a lot of money. But what we do, or what they do, is they use what we call these what? Brushless DC motors. But these guys have to be electronically controlled. And you can see what's happening. They electronically shift the field inside here. What does this magnet on the outside do? It follows. So it's a lot like a stepping motor, but a brushless DC motor is. And with the gearing that we have available in the technology of brushless DC motors has really increased. There's a lot of power hand tool equipment that's going to brushless DC motors. Have you ever used your battery powered drill and looked in that thing and watched that sucker sparking when you hit that? Well, every time that thing sparks, it generates electromagnetic interference. So the biggest advantage of this brushless DC motor is it's got what? Almost no what? So this is why inside your computer, all your fan motors, we could rip off any fan motor inside a computer and it would be a what? It would be a brushless motor. If you got hard disk drives inside your computer, it's going to be a brushless DC motor because it basically eliminates the motor generating EMI. Yeah. With gears, it depends on, remember, if we come in and we can run these things at extremely high speeds, then we can use gears to get the torque, right? You understand? But what we have to do is we decrease speeds, and hand drills don't run real fast. So if you ever looked at the little DC motor inside a power drill, it's not that big anyway. So where do we get our torque at? Through gear ratios. Yeah, we just go and make the gears, a big gear run a small gear run a big gear, and we get all our torque. It would surprise you how small the motors are that's inside your hand tool. So yeah, brushless DC motors are becoming very popular inside some of your hand tools, and that's a selling feature. What I would, but it's electronically controlled, so they don't get. It's easier to control the speed, right? You understand? Most of your hand drills controls the speed with just a resistor. And when we say resistor, what does that mean? What type of work does a resistor do? Heat, right? And it's just wasted, resistors are just wasted energy. That's all they are, just wasted energy. That's all they are. So yeah, if I can electronically control the thing, which with these switches, then switches are very, very efficient, right? You understand, which means you get a longer battery life out of your hand drills. So that's why some of your more expensive hand drills are going to these brushless motors, and they run them at a real high speed, right? You understand, and then they get their torque out of what? Out of that gearbox in the front. But now your batteries will last not a little bit longer, a long time. Because you have very little wasted energy in the circuit that's controlling the speed, right? You understand? Yeah, you don't need resistors in there. So guys, that's all the DC motors. And then what we'll do is we'll get into AC motors. But what we're going to do now is we're going to go ahead and try to finish up our lab. Let me bring this back up real quick. So, well, what we're trying to do is we're trying to do a function chart, right? It's a shame when you got to set alarms so you don't forget to do things. And we're working with the Amatrol line. And we'll bring up the module that they're not doing. So this is basically what a function chart should look like. So basically, the first step is supposed to be what's required to start, right? Of course, we don't put power, so every one of y'all should have water. Start, the green button that you do that you press, and then of course the position that the line is in before you press the start button, right? Huh? Yeah, the end should end up in the same spot, right? You understand? Unless we have it in auto mode, which they don't show. What they're showing you is what it does when you do the step. If we have it on auto mode, then what would it do? It wouldn't wait on the start, but this over here would still have to be what? True. You don't need to worry about the end. This just says nothing's actually, I'll have to look that up again. But then what you do is you come over here and you're supposed to put the output that causes it to happen, right? You understand? Does that make sense? And then you're supposed to put the sensor that it affects. Huh? Oh, yeah, y'all can leave this off right now because y'all don't have the diagrams on the PLC, because you'd have to have the diagrams. But what we need to do on ours is say, okay, what is required and this is what's required to go to the next step. So whatever you put over here should be what? Should be right there. And y'all don't need to know the inputs. We'll come back and see that. So what we'd have to do to actually do the inputs is we'd actually have the diagram. We'd have to actually have the PLC diagram, right? Okay, guys, let's go.